All right, this is question 5. You might have noticed I've had to stop and start the video a few times. I apologize for that. Question 5 in your test is written as question 7 on the mark scheme. And this is all about total internal reflection. The question shows you a glass block and you have light going into this glass block and coming out of it. So what I want to do is go through these points. You've got to say which ones are right or wrong. What do you know about refraction and total internal reflection? So here, light changes speed when it is internally reflected. No, it does not, because it stays in the glass and light goes the same speed if it doesn't change medium. It will stay the same speed in air unless it goes from more dense air to less dense air. But if it changes the medium, it changes speed. If it doesn't change the medium, it's not going to change its speed. Every ray entering the block is reflected by total internal reflection. No, it might have an internal reflection, but not everything is going to be total internal reflection. That light might come in and some of it be refracted. So, nope, that is not correct. Whoops. If I equals 0, the ray does not deviate. So if I becomes 0, then your light is going to go directly on at right angles to the surface. Your instant angle is 0, it will go straight out again the other end without any deviation. So yeah, that's true. If the refractive index of glass is bigger than the refractive index of air, yes it is. The refractive index N of glass is around about 1.5 and air it's about 1.0. So the next ones. You have to complete the path of the light through the jewels. Some of you got this right and you can see in the mark scheme kind of how you get the marks. This is what's going on and this is why. If you have any ray of light hit glass at 90 degrees to the surface of the glass, so the angle between the ray and the normal is 0, it will go straight through. I is 0 degrees. It will go straight through without any bending at all. And exactly the same on this way around. It's coming out at 90 degrees, so it must have gone in at 90 degrees. Let's just use that, and it will get us most of the way, halfway through this question. So, if, whoops, it could be better than that. Let's do it. Here, that line should go straight through and then straight out again because it's at 90 degrees, and that should go straight through and straight out again. It's 90 degrees. Now, let's zoom in a little bit and have a closer look. The angle here, let me do it in a different color, so we're having our rays one color and annotations another. This angle between the ray and the surface should be exactly the same as the angle that the ray comes out at. So let's keep the colors the same. Let's have another straight line. That must be around about like that, and you can see that it's actually meant to match up with this one. And what happens is the path of light in total will go along here, bounce there, and then along there again. Gets you 3 marks. Show by calculation that the critical angle for refractive index is 1.5 is 42 degrees. You need to remember this equation. Sine of the critical angle C is equal to 1 over the refractive index N. That's an equation you need to memorize. You should know that one. We did that one relatively recently. So how do we do this on our calculator? Well, 1 over N is 1 over 1 divided by 1.5. 1 over 1.5. And 1 over 1.5 is 0.666 recurring. So sine C equals 0.666 recurring. How do you get to C? There's a function on your calculator that will do this. It's called inverse sine. So you would do inverse sine of 0.666 recurring, or 1 over 1.5. 1 over 1.5. So I'm going to do it like this: sine inverse. I don't think that's going to work. Question mark. Let's try again. Sine inverse 1 over 1.5. Ooh. small mistake there. It's come up with takeaway 5. Let's do that again. 1.5, please. Yes, it's worked out. 41.81, so on and so on degrees, which is close to 42. So whenever you have a show or a show that question, you're not allowed to use your answer. You have to get to that answer. You can't use the 42 to get your answer. You need to show that the answer is going, it's never going to be exactly whatever they tell you to show, whatever they say show that is going to equal to. So it's always going to be around about whatever that you've got to get to. It's going to be around about 42 degrees. In this case, it's 41.8 degrees. And then you can say that's approximately equal to 42. But show this number. Show the number on your calculator with all the decimal points, because then it shows that you've actually got a value. So, sorry, we didn't actually look at the mark scheme for this. Let's have a look. So it says here, yeah, 41.8 degrees. If you've written that down somewhere, it's worth 3 marks. So the next question says, explain why the quantity called refractive index has no units. It has no unit because any value, if you take any value, n is sine I divided by sine r. If you did something that has imagine this is a piece of paper and you've got A and B, and you wanted to work out a value x that was A over B. Any value that you work out that has the same units on the top of a divide sign and the bottom of a divide sign cancel out. So if this was measured in centimetres and this was measured in centimetres, then your unit for x would be centimetres per centimetres. Centimetres divided by centimetres or centimetres per centimetre cancel out. There is no unit. So x would have no unit. Here, sine I divided by sine r has no unit because the two cancel out. Also, sine I doesn't have a unit either because sine is a ratio of one side of a triangle to another side of a triangle that you might have done in maths. So sine I doesn't actually have a unit of degrees. It's actually not got a unit either. So you've got something that hasn't got a unit divided by something that hasn't got a unit. You still don't have a unit. So you need to say that that both of them are unitless. And you divide a unitless thing by a unitless thing, you're still going to get a unitless quantity. The next part of this question is you've got to add a point to 1.5, 42. So 1.5 is there, 42 is there. Add this point here. And how can you tell that that point is not anomalous? Well, you can say it's not anomalous because it fits the pattern. It fits the pattern of the data. You can see that quite clearly. I'm just going to pause it there. Hold on 1 second. Okay, picking up where we left from, this point fits the pattern. Whoops, why have I put an apostrophe in there? Fits the pattern. You can see that the graph carries on and it's going to not deviate by adding that point. So that will get you the mark. But 2 marks here is you've got to explain why the axes don't start from 0. Well, the first thing is, if they did start from 0, imagine they start from 0, 0, went up to 2.5 and 45, all of your points would be in one corner. And so, you know, you'd have a lot of free space here that you wouldn't actually need. So essentially, you need to say something about this point here that they've got in the mark scheme. The idea that a reduced scale gives a fuller use of the grid. So you're using the paper to the max. Okay, you're using the paper fully is the kind of idea they're going for here. Another thing is the refractive index for air is 1, and the refractive index for all other materials that light goes through is going to be greater than 1. So you can say all n's are greater than 1. So you're not going to, there's no point in putting points from 0 to 1. It doesn't exist. And the critical angle, there isn't really a low critical angle. There's no such thing as a critical angle of 0, because that would, because if I, and this is your glass or any material and this is air, if I is 0, then the light is going to go straight through to the air. It won't bounce off that surface. It's not a mirror. So if there is no such thing, there's no critical angle equal to 0, or all critical angles are greater than 0 degrees. They have to be. It says in the mark scheme that angle of critical angle has to be greater than around about 20 degrees. You don't need to memorize that. In the mark scheme it says there is no critical angle that's 0. So you're okay just to say no critical angle 0. For the next part, oh sorry, I've already put loads of answers in here. I tried to record this before and there were some massive errors, which is why there's been a delay in me getting this video out. I do apologise. Let me just remove those. So this is the motor question, and you can see that the first part of it says, what is DC? DC, direct current, is current that only goes in one direction only. What is the purpose of the brushes and the commutator in a DC motor? The brushes and the commutator ensure an electrical connection. And they reconnect. They reconnect every half turn. They make sure that the motor keeps on spinning in the same direction. By making sure that the force on one side is the same as the force on the other. So here you've got your motor. Let's split it off into two sections, one section there, another section there, and it makes, having a commutator and a brush makes sure that that one side is always pushing up, another side is always pushing down. So forces always pushing up on one side and down on other. And remember what I keep on saying, it's okay to do a diagram. A diagram helps explain what's going on, and it shows the examiner that you really understand it. So forces always pushing up on one side and down on the other. Just in case you've written something that doesn't 100% make sense, the diagram might help the examiner make sure that you understand what you're talking about. The motor turns clockwise. Oh, let me just double check that this is worth all the marks. There's a lot of marks here in the mark scheme. Provides a connection, yes. Reverses the current in the coil so that every single half turn it reverses the current. Saying something about every half turn, I've said reconnecting every half turn, that's fine. Reversing the coil's polarity every half turn, yep. So that the force is always in the same direction. Force is pushing up on one side and down the other all the time, so that the motor keeps on turning, the motor keeps on spinning. Yeah, these are 6 different points that you could have said. For the next part, the motor turns clockwise when the direction of the current goes from positive to negative. So it starts off going clockwise. What happens to the motor when the magnetic field and current are both reversed? Well, if it's going clockwise and then you swap the positive for the negative and the negative is positive, it's going to go the other direction. So if you go from positive and negative swapping, it will go anti-clockwise. But then if you also swap the magnetic field, so the north and south poles are swapped around, then it will go back to clockwise again. So the answer is it stays going clockwise. The next question, part B, again, sorry that I've already put the answers in here. The photo shows a machine at a coal mine. The machine lifts up containers of coal from the mine and lowers the containers down. The machine uses an electric motor connected to a 600 volt DC supply. Make sure you circle all your numbers, 600 volt. 600 volts and 4,000 amps I can see written down here. Remember that you should remember that amps is current, volts is voltage. That's an easy one to remember, but amps being current, sometimes people forget. State the equation linking power, current and voltage. Well, power equals current times voltage. And the symbol for current is I, another strange one. So power equals current times voltage. Calculate the maximum power available from the motor. P equals IV, so it's going to be 4,000 multiplied by 600, and we get, using our calculator here, hopefully 2,000, hold on a sec, not 2,000, 2,400,000 watts, which shows you that 1 watt is not very high. But you've got to put your answer in megawatts. You need to remember that mega is a bit like a million. The actual word for it is mega, not million, but it's a bit like a million. So here you got 42,400,000 watts. So that's going to be 2.4 million watts or megawatts. The next question is, get rid of this, get rid of this, get rid of this. The next question is, what is the equation, work done, force and distance? Well, you should know this. Work done equals force multiplied by distance. You need to know that equation. So the mark scheme says work done equals force times distance, but you can, for all of these equations, you can always just use the symbols. And I get used to using the symbols, it just makes it quicker. Calculate the work done. Well, you've got a force and you've got a distance, and your forces and your distance are in the correct units. They should always be in newtons and meters. Work equals 400,000 multiplied by 190. 400,000 multiplied by 190. It's going to be a massive number. 76 million joules. So that's W for work, not W for watts. I mean, sometimes people get confused. This is energy. Remember that energy and work are the same thing. So 76 million joules. I could also just say, I could say 76 megajoules. And that gives me my answer. The machine uses a mean power of 1.9 megawatts to do 67 megajoules of work. What is the time needed to do this work? Well, the time equation for, the equation for time and power is here. Right at the very beginning, power equals energy divided by time. Let's go back to our question, which is page 18, I think. This one here. Calculate the time needed to do this work. Power equals work divided by time. Rearrange this equation and you get time equals work divided by power. So we have work is, not left a lot of space to do this, time is 67 megajoules divided by 1.9 megawatts. Now, because the mega means million, and that's a million, you're doing a million divided by a million, you don't have to actually convert. You could just leave your values as they are, 76 divided by 1.9, and you're going to be fine. Sorry, I said 76, I meant 67 divided by 1.9. And you get an answer of, this calculator is not as good as I thought it was. Go away. Okay, let's try this again. 67 divided by 1.9 equals 35.3 seconds roughly. And mark scheme says 35 is worth 3 marks. And the middle marks are for rearrangement of the equation, so that part there, and for substitution, and then the last mark is for the actual correct answer. State the effect of using a lower average power to do this work. Okay, so here we've got a value, a lower average power. Our power is 1.9, so have a look at the calculator on the right. Imagine it wasn't 1.9, it was a lower power of 0.9. What's happened to the time? It's gone up. It's gone to 74 seconds. Well, you're not changing the amount of energy or the amount of work that you need to do. So the time increases. And if you're not sure, you can just plug in values into a calculator and see how it changes your result. For the next question, so let me get rid of all this. The next question, this is the one that stumped a lot of people. This was a quite complicated question, and it's a scientific inquiry type question. The scientific inquiry type questions essentially mean that you need to understand how to do experiments, and you need to know what variables are, you need to know what things can go wrong, how to make improvements, how to compare one way of doing something with another way of doing something. So this whole question is about measuring the circumference of a circular pipe. They couldn't have picked anything more boring. So the string is wrapped around pipe, and it's wrapped around 5 times, and it's marked with ink as shown in the photograph below. The student unwraps the string and holds it against a ruler with a centimetre scale, and the next photo shows the 2 ink markings on the string. I'm going to highlight them. There's one there, and here's the other one there. And the next question you're going to get is, what is a circumference? So you need to remember that circumference is the distance around a circle, and that's going to be the same in this idea as the string going around the actual site outside of it. So from one dot to another dot is going to be our circumference. And this one, I can kind of see, it's quite difficult to actually read the scale. It's between 41 and 42. I think it's this value here, and I think it's 41.9. And here, this is a really hard one to read because it's kind of right in between 47.3 and 47.4. I'm going to say 47.3, but can you see the thickness of the dot is actually a problem? And actually that's going to be important for the question later on. I have just written down 41.9. Oh yeah, which is correct, 41.9. So what is the circumference? Well, it's going to be 47.3, take away 41.9. And that is going to be 47.3, take away 41.9, 5.4? Yeah, 5.4. The mark scheme, let me see if I can pull up the mark scheme here on the right-hand side, allows you to be 0.1 out. And if you're 0.2 out, you lose 1 mark. So that was a 2-mark question. And getting it good and getting it accurate gives you a mark, an extra mark. The next part, part 2, the student finds the total length of string for 5 turns is 25.6 centimetres. That sounds about right. It's almost 5 times this value. Calculate the mean circumference of the pipe using this value. So you take the string and you wrapped it around, then you wrapped it around again, then again, then again, then again. That's 5 turns. That total length unwound 5 is going to represent 5 times the circumference of your string. So 25, whoops, not 2.5, 25.6 divided by 5 will give us the circumference of the string, which should just be for 1 turn. 5.12 centimetres is perfect. So remember that 25.6 is 5 turns, and so we're trying to work out whatever 1 turn is, and it's 5.12. The mark scheme, you can see it right there. This is the mark scheme. It says 5.12. It's for clear as day. There's no error allowed for this answer. The next question is to measure, oh no, the student measures the diameter. I should read the question. Listen to my own advice. Read the question. The student measures the diameter of the pipe using a digital caliper. Even if you've never used one of these before, and we don't even have them in school, so I know that you haven't used them before at school. A digital caliper, you can automatically see this is probably a bit more accurate than using a piece of dirty string. The caliper shows that the diameter is 15.10 millimeters. Calculate the circumference of the pipe using the formula that they give to you that you should already know from maths. Circumference equals diameter times pi. Calculate the circumference in centimeters. First thing I'm going to do is, I don't want to avoid any unit errors. I'm going to convert that value of millimeters into centimeters. 1.51 centimeters is our diameter. And you can see it on here, 10 millimeters is 1 centimeter. So you can convert to centimeters that way. So I've got to do that times pi. 1.51 pi. There you go. 1.51 times pi equals 4.743 and so on and so on. So the mark scheme says 4.744, but 4.74 is all okay. And it depends on what value you're using for pi, what your third decimal place is. So the mark scheme here has got 4.744. I think that's because they're using 3.142 instead of 3.14159265535. You know, the correct answer for pi. The next part is B. The student uses two methods for finding the circumference, averaging using the length of string and calculating using the digital caliper. 4 marks. Let's spend a bit of time having a look at this. String method, you've got to talk about why these two methods are likely to give different results. So the string. The first thing we already noticed was the dots have they have a thickness themselves. And the thickness is about 1 millimeter. So if you're measuring from one dot to another dot, then that might be a millimeter out, that might be a millimeter out. So your total length from one to the other is going to be about 2 millimeters out. That's not really very good. So dots have a thickness of about 1 millimeter anyway. The second thing is to notice that, I'm going to try and draw a circle here. If you have a pipe like that, and you're taking some string and wrapping it around the pipe to work out how wide the pipe is. Say I take some string and I go like this. The string is going to go around the outside. So the string has a thickness. So you're going to get a bigger value. As it goes on the outside of the pipe. So that's one really important point to make. So the first thing is about that. We're going to make those 2 points, and I'm going to have a look at the mark scheme in a moment, but let's just go back to our caliper. So caliper. Well, first of all, we want to make sure that, value for pi there might be an error in our value for pi, because we can see here the value for pi that they're using isn't the same as the value for pi on the calculator above. So there might be a problem with the value for pi. A few other things to mention about the caliper is why they're going to get different results. Well, you can say that the caliper is obviously to a higher precision. And explain exactly what you mean by this. It measures to 1/100th of a millimeter. So you're going to get a better result in terms of precision because your values are actually going to be a lot higher. But there are a few other things to point out. You're only measuring the diameter and you're assuming it's a circle. We haven't had to assume it's a circle for the string. It could have been a slightly oval shape. So we're assuming it's a circle when we use that equation. Those are problems. So I've mentioned a few things. Let's see how mark-worthy they are and see how many other things are in the mark scheme. So different precision. I mentioned that about precision. Calculation error, value for pi. Unskilled use of equipment for a third point. So what do they mean by that? There's more information here. So unskilled use of equipment may not have drawn the dots in a straight enough line. Very good point. May not have the caliper at 90 degrees. May crush the pipe with the caliper. All right, I like this one here. The there's a point here about can't do a true circle. So what I want to point out about the string method is actually you are making a helix, because you're wrapping one around another one, around another one, around another one, and the string starting point and the ending point don't end up at the same point. They end up stretched outwards, a bit like the DNA double helix. They end up stretched outwards like a coil and spring, so the value that you're going to get for the length is a little bit longer. So that's what this means. You can't do a true circle with the string method because you're going to do a helix instead. The width of the pen mark, so dots have a thickness of about 1 millimeter, which is the same as width of a pen mark point. The string could stretch. The string has a thickness which makes the circumference larger. We've mentioned that in the point I've written in red. There's a parallax error when using the ruler because the ruler and what you're measuring are not in the same plane. There might be a zero error for the caliper. So just like every measuring instrument that's electronic, you have to make sure you've zeroed it. Before you put something on weighing scales, you have to make sure that the weighing scales say 0. If they don't, then you're probably not going to get the right answer. The pipe could also be damaged. So there's a lot of things you could have said to get those marks, but it's still a very difficult question. The next question, sorry again for all the working out. Oh, it's not even rubbing out properly. Rub out. Okay, good. Better. This question says, an underground train enters the station. The mass of the train and the passengers is that. The total kinetic energy is that. State the relationship between kinetic energy, mass, and velocity. Before I do that, I'm going to convert that into joules. 18 million joules. We don't convert kilograms into grams. Mass always stays in kilograms. Energy is always in joules, and nothing else should have any prefix. There shouldn't be any kilo, or mega, or milli, or centi in front of anything apart from mass. It's the only one that stays with a prefix of kilo for kilograms. So this one is Ke equals a half mv squared. We should know that. And like I said, you can carry on using abbreviations like m and v for mass and velocity. So here, K equals half mv squared. Calculate the velocity of the train as it enters the station. So if you wanted to, you could try and rearrange the formula. So if we multiply both sides by 2, we get 2 lots of kinetic energy equal no longer half because you multiplied by 2. You've got mv squared. The next step is to try and get velocity by itself. So we're going to keep velocity where it is, and we're trying to get rid of mass. So if we divide both sides by mass, because you have to do the same thing to one side and the other side, you can see here that mass divided by mass cancels out. And if something is, if you've got v squared and you just want to find v, well, you root the whole lot. And the root of if you square something and then root it, that cancels it out. And you've got the equation appearing here on the left-hand side. So to plug in these values, the root of 2 multiplied by, oh, it's our big value, 18 million, divided by 250,000. Oh, let's see if we can do this up here. 2 times 18 million. Good. Divide it by 250,000. Good. And root the whole lot. And the answer is 12 meters per second. Do show your calculation steps. You get 1 mark for, let me just highlight them, 1 mark for this, rearranging, substitution and rearranging. Oh, you get 1 mark for that, conversion of units. And then you get 1 mark for the calculation and getting 12 out at the end. So that's how you get your marks. Driver applies the brakes. What happens to the kinetic energy of the train? Well, it's going to decrease. But what they're really asking for is what happens to it? Where does it go? Well, it's going to kinetic energy is going to go down and it's going to get converted into something else. Kinetic energy of the train gets converted into heat and sound. in the breaks, in the surroundings, in that kind of stuff. It says here, energy is transferred to the surroundings, but if you say energy to heat and sound and other forms, that's fine. The next question says, oops, get rid of. The passengers who use the station are carried from platform level to street level in a lift. Why do they gain GPE in the lift, even when they're below ground? Well, they gain GPE. You need to know the GPE equation, really. Otherwise, you can't really talk about why they're gaining GPE. So GP is mgh. These stay the same. H increases, so GPE increases. And it's okay to put your answer like that. You don't have to just do paragraphs and sentences and prose. It actually makes more sense to do it like that. Look at the mark scheme here. GP equals mgh. I've written that down. Passengers have moved to a higher point. H increases. So higher point. Its height has increased. And that gets you my 2 marks. You could have also said the work done to move. There is work done to move the passengers, and passengers are further from the centre of the earth. The next question. Okay, this is about entering and leaving a station, and you can see that in the diagram on the previous page, go back to it for a second, that the platform is higher than the tunnel. So when the train goes into the platform, the train must go up, and when it leaves the platform, it must go down. And so let's split this up. 4 marks. Entering. We'll do a section for entering and a section for leaving. So when the train enters, what's going on? Well, it's got a lot of kinetic energy. It's got to get rid of its kinetic energy. So it has lots of KE, and it's got to get rid of that KE. Well, if it goes up, travels up, so some of that kinetic energy gets turned into GPE. So as it's losing kinetic energy already because it's going upwards. And that means that brakes have to do less work. Okay, imagine you're on a bike and you're cycling and you go towards a hill that's going upwards. As you just coast along, you'll end up stopping without even using your brakes. And that's what's going on here. The train goes upwards, so the brakes don't need to even go on. Or if they do go on, they don't have to go on for as long. They don't have to be used as much. So the brakes have to do much less work. And you could say easier to stop. You could also say it stops quicker, and so on and so on. Leaving, so lots of K at start. Sorry, I've just realised I've written that down. Lots of K at start, you're trying to get rid of it. So leaving, so train moves down, and that must mean that the GP it gained by going into the station gets turned into kinetic energy. So it picks up kinetic energy from the fact that it's actually moving out of the station even without needing to use the motor. So the motor needs to do less work. Much less work. Doesn't need to. And then you could say it's easier for the train to move faster, or the train would move faster, or it takes less time to get to the same speed. What else have we got here? I'll leave the mark scheme on the right hand side. If you wanted to have a quick look at it and pause it, then you can do. So there you go. It's there. If you want to have a quick look and go into more detail, you can. The next question is question 9. This was a question that people found very difficult, to be honest. It was very hard. It seems easy, but it used an idea that we've gone through a lot of times in the past and maybe too long ago. The photograph of a polar bear was taken using visible light. Diagram shows thermal image of the same scene. Darker colours indicate lower temperatures. Cold. Warm-ish. Hot. So darker colours indicate lower temperatures. Discuss what information in the image is given about the temperatures of the objects shown. Well, you can see the sky is coldest. Colder and bear. You say the bear, well, the bear's eyes are hottest thing in picture. And the bear's fur is about the same temperature as the snow. The thing that a lot of people messed up on with this question was all they really wanted. You can't say if something is hot or cold or warm. Like, this is not really good enough, because if you touch the snow, it's not going to be warmish. It's not going to be warmish. They're really asking for comparative sentences. So how can you say that? You can't say which one is cold and hot and warm. You can say that, well, actually the sky is colder than the snow. You could also say that the polar bear's fur is the same temperature as the snow. You could say that the eyes are hotter than the rest of the polar bear, but you can't say exactly what the temperature is. So don't say that one temperature is hot or cold. Say a comparative sentence, and they're there on the right-hand side for you to have a look. Part B. Polar bear's fur includes short hairs and long hairs. Long hairs are hollow and contain air. Explain how its fur reduces the amount of thermal energy lost by the polar bear. 2 marks. How is the amount of thermal energy lost by the polar bear decreased? Well, okay, the first thing is air is trapped by the fur. Air is insulating. It's an insulating material, really. It's not really a material. It's an insulating. It insulates. It essentially isn't very good at conducting. Does not conduct heat well. And you can also say, as air is trapped, it can't move, and therefore you can't transport heat around using convection. So you can't create convection circuits or convection currents. So all of those things go towards keeping the polar bear warm, and how its fur is basically reducing the amount of thermal energy lost. So there are other things you could say as well. And on the mark scheme, you've got the hair is an insulator, the air is an insulator, the air is kept trapped near the body, convection currents can't form. White fur is a poor emitter of thermal energy, or infrared energy. Underneath its white fur, the polar bear has black skin. So what is going on here with these colours to affect the amount of thermal energy lost by the polar bear's body? You're right in thinking that these colours are actually going to help the polar bear. But why? So first of all, white fur reflects. And actually, we spoke about the things that can happen to infrared radiation in a lesson, and we spoke about reflection and absorption. We also spoke about emission. And transmission. So these are the things that can happen. Reflection is bouncing off a surface, absorption is going in, emission is coming out, and transmission is passing through. So you need to remember that for infrared radiation, surfaces that are white are very good at reflection, and they are pretty bad at the others. Black is very good at absorption, emission. Black is very good at that as well. Transmission is essentially absorbing and then re-emitting, so black is very good at that too. So how do these ideas contribute to getting 3 marks in this question? So white fur reflects, yes. And black skin is good at absorbing and emitting. Yes, that's the basics that we need to start off with. So you could say that the black skin emits infrared heat or thermal radiation. The white fur, which is above the black skin, then can reflect that infrared radiation back towards the polar bear. And then the black skin will then reabsorb it. So any infrared radiation that hits the polar bear and gets into the polar bear past the actual fur will go right the way through and be absorbed by the polar bear. But what's really going on here is the black skin will emit infrared radiation, the white fur reflects it back to the polar bear, and then the black skin will then absorb it again. And the marks are there on the right hand side if you wanted to go through in detail and have a quick look at that. But by saying that black skin is a good emitter, white fur is a good reflector, and black skin is a good absorber, by just saying that these basic points at the top, that gets us 3 marks. The next part, part C, is an image taken using UV. So this is about UV, not infrared. Brighter colours indicate large amounts of UV radiation. So lots and lots of UV is coming out here. And obviously some from the eyes. So lots of UV is being received by the camera. Compare the absorption and reflection of ultraviolet rays by the objects shown in the image. A lot of people mess this up. So if the camera is receiving lots of UV, it must be because UV is not being absorbed by those objects. If you have UV going into that object and staying there, it's not going to come out again. So UV is being reflected off the snow and the eyes, or being given out by the snow and the eyes, which is not the case. It's actually being reflected. So the sky must absorb UV. The fur on polar bear must also absorb UV. Because nothing's being reflected. You're not getting any. The camera's not picking up any from the bear. So if it's not picking up any, then it must be that any UV that hits the polar bear is staying on the polar bear. So the snow reflects UV. And back to the camera. Suggest why the sky appears dark even though the sun emits UV rays. Well, the sky appears dark because the sky is absorbing UV. There's stuff called ozone in the atmosphere, in the sky, that absorbs lots of UV. Also, the sun is not in the picture. It's not in that photo. And that gets you all your marks for that part. The hollow hairs in the polar bear are transparent tubes filled with air. This is a really tricky part. There's a last question. You've got to essentially discuss why this doesn't happen. Why doesn't total internal reflection happen down a hollow tube? It doesn't happen down a hollow tube because it doesn't happen in air. It happens inside glass. And it happens inside materials that are more optically dense than air. So if I have here a hollow tube, and indicate that it's a tube by actually having some kind of material here, and I have here glass, then they act very differently. The glass will bounce, the infrared radiation will go through there, but here there won't be any bouncing. This isn't possible. So what's going on that means that that isn't possible? Essentially, for total internal reflection to happen, the values for the refractive index must be high in the material where you want the total internal reflection to happen and low outside it. So here in glass, refractive index is around about 1.5, and in air it's 1. You must be going from a more optically dense material to a less optically dense material for total internal reflection to happen. So TIR not possible, because it only works when N goes from high to low, and that's not the case here. It's happening in another way. So the more detail is in the mark scheme. I'm going to leave that for you, and I think that's the last question. Thank you very much, and sorry that the video's been delayed, but I had a problem with the recording not working properly. Thank you.